US Physics Olympiad, year 2014, USAPHO. Final exam. Problem A2. A room air conditioner is modeled as a heat engine run in reverse. An amount of heat QL is absorbed from the room at a temperature TL into cooling coils containing a working gas. This gas is compressed adiabatically to a temperature TH. The gas is compressed isothermally in a coil outside the house, giving off an amount of heat QH. The gas expands adiabatically back to a temperature TL and the cycle repeats. An amount of energy W is input into the system every cycle through an electric pump. This model describes the air conditioner with the best possible efficiency. Assume that the outside air temperature is TH and the inside air temperature is TL. The air conditioner unit consumes electric power P. Assume that the air is sufficiently dry so that no condensation of water occurs in the cooling coils of the air conditioner. Water boils at 373 kelvins and freezes at 273 kelvins at normal atmospheric pressure. Question A. Derive an expression for the maximum rate at which heat is removed from the room in terms of the air temperatures TH, TL, and the power consumed by the air conditioner P. Your derivation must refer to the entropy changes that occur in a Carnot cycle in order to receive full marks for this part. Solution. As we see from the description, this cycle consists of two adiabatic and two isothermal processes. During adiabatic processes, the heat is not transferred. It means that full entropy change is zero. And also during whole cycle change of entropy is zero, because this is a Carnot cycle, and we can write by definition what is the change of entropy. Change of entropy ds equal dq over T. In our case, we have two adiabatic processes where dq is zero, and we have two isothermal processes with a constant temperature. And because total change of entropy is zero, we have this equation. We have Q high over temperature high equal Q low over temperature low. Also we have energy conservation. We have Q high equal Q low plus work done over the system W. From these two equations we can eliminate Q high, and we will get Q low equal W multiplied by T low over T high minus T low. And this is all what we need. Now we just need to divide this Q low over temperature to get the rate with which this heat is removed from the room. This will be QL over time T, which is equal power multiplied by this coefficient. This is the answer for question A. Question B. The room is insulated, but heat still passed into the room at a rate R equal K delta T, where delta T is the temperature difference between the inside and the outside of the room, and K is a constant. Find the coldest possible temperature of the room in terms of TH, K, and P. Solution. We already found that K dt, the rate with which the heat is removed, that's equal QL over T, which we found in the previous question. That was P multiplied by TL over TH minus TL. But denominator, that's dt in our terms. And the TL we can express through TH minus dt. So from here we can do quadratic equation. So for this equation we have a solution in this form, and only positive root has a physical sense. So we can find what delta T, and after that find what is lowest possible temperature. That will be this expression. That's the answer for question B. Question C. A typical room has a value of K equal 173 watt per degree Celsius. If the outside temperature is 40 degrees Celsius, what minimum power should the air conditioner have to get the inside temperature down to 25 degrees Celsius? Solution. From this quadratic equation we can find what is this power. That will be this expression. Now let's put numbers. So in our case delta T equal 15 degrees and the lowest temperature equal to 25 degrees plus 273 to convert Celsius to Kelvins. And totally result will be 130 watt. That's the answer for question C.